Okay, in today's lesson we have a lot to cover. We're going to be able to identify properties of rational functions and to graph rational functions, and that deals with a lot of information. First of all, we have our warm-up, so I want you to pause the video and factor problems 1 and 2, and then factor and solve problems 3 and 4. Then restart the video to check your answer. Okay, factoring the top two, the signs are going to be the same. Both of those are going to be positive. Factors of 6 that add up to be 5. Again, the signs are going to be the same. They're both going to be negative, so factors of 8 that will add up to be a negative 6. The different signs, the largest factor will be positive. Same signs, they'll both be negative, so factors of 18 that add up to be 9. Our key concepts. A rational function is a function that you can write in the form f of x is equal to p of x over q of x, so written like a fraction, where q of x cannot equal 0. A continuous graph is a graph that has no breaks, jumps, or holes. That means that you can draw the graph without picking up your pencil. A discontinuous graph is a graph that has jumps, breaks, or holes in it. A point of discontinuity is the point at which the graph is not continuous. So it would be that hole or that jump or that break. There are steps to find points of discontinuity. First of all, you're going to factor if possible. Set the denominator equal to 0 and solve for points of discontinuity. If a point of discontinuity is a factor of the numerator, then the function has a removable discontinuity, or x equal a is a hole. If a point of discontinuity is not a factor of the numerator, then the function has non-removable discontinuity, or x equal a is an asymptote. For example, we're going to use this rational function to find what the domain is. So first of all, we're going to factor the denominator. We're going to set the denominator equal to 0 and solve it. So we find that for the denominator, x is equal to 4 and x is equal to 3. Since the function is undefined where x is 4 and x is equal to negative 3, the domain is all real numbers except for 4 and negative 3. Now let's look to find any points of discontinuity and if they're removable or non-removable. Well, since neither one of these are a factor of the numerator, there are 2 points of non-removable discontinuity at x equal 4 and x equal negative 3. To find the x-intercept, we're going to set the numerator equal to 0 and solve. And to find the y-intercept, we substitute in a 0 for the x. So we discover that our y-intercept is at 0, negative 1/3, and our x-intercept is at negative 4, 0. Okay, let's look at this example. What is the domain of this function? Well, first of all, we can't factor it. If we set the denominator equal to 0, we come up with a complex number, not a real number. So that makes the denominator, since no real number makes the denominator 0, the domain is all real numbers. There are no discontinuities. If we set the numerator equal to 0, our x-intercept is at 0, 0. And then we substitute in a 0 for the x values. We get 0 over 12. 0 divided by 12 is 0, so our y-intercept is also 0, 0. Another example. To find the domain, first of all, we're going to factor the numerator. Look here, we got common factors, don't we? We're going to set the denominator equal to 0 and solve. So since the function is undefined, where x is equal to negative 2, the domain is all real numbers except negative 2. There is points of removable discontinuity at x equals negative 2 because both of these are factors of the numerator and the denominator, so it's removable at x equals negative 2. To find the x-intercept, we're going to set the part of the numerator that's not also a factor of the denominator, just this x minus 2, we're going to set it equal to 0 and solve. So the x-intercept is at 2, 0. We substitute zeros in for the x's to find the y-intercept. Negative 4 divided by 2 is negative 2. So our y-intercept is at 0, negative 2. Vertical asymptotes. The graph has a vertical asymptote at x equal a if it has a non-removable discontinuity at x equal a. What are the vertical asymptotes for the graph of, looking at our first function? Since negative 2 and 3 are roots of the denominator, but they are not roots of the numerator, the lines x equals negative 2 and x equals 3 are vertical asymptotes. Oh, look here, we've got common factors. So since negative 2 is a root of the denominator but not a root of the numerator, the line x equals negative 2 is a vertical asymptote. And since negative 7 is a root of the numerator and denominator, there is a hole at x equals negative 7. Horizontal asymptotes. In order to find them, you compare the degree of the numerator to the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, there's a horizontal asymptote at y equals 0. If the degree of the numerator is equal to the degree of the denominator, there's a horizontal asymptote at y where it's the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. So let's see what that looks like. Here we both have a degree of 1 in the numerator and the denominator. So the horizontal asymptote is at the ratio of the coefficients of the leading term, negative 4 over 2, or where y is equal to negative 2. Numerator is a degree of 1, denominator is a degree of 2. Since the degree of the numerator is less than the degree of the denominator, there's a horizontal asymptote at y equals 0. The degree of the numerator is 2, the degree of the denominator is 1, so there is no horizontal asymptote since the degree of the numerator is greater than the degree of the denominator. Now, steps to graphing a rational function. First of all, we need to find the horizontal asymptote, if there is one, and using the rules for determining the horizontal asymptote of a rational function, which we just did. Factor both the numerator and denominator. Find any vertical asymptotes by setting the denominator equal to 0 and solving for x. When I graph my asymptotes, I tend to graph those with a dashed line to indicate that they're different. And I also write the equation of the line with the dashed line. Find the y-intercept if there is one. Find the x-intercepts if there are any by setting the numerator equal to 0. Then find a few more points on the graph. So let's graph this rational function. First of all, find horizontal asymptotes. The degree of the numerator is 1, the degree of the denominator is 2, so the horizontal asymptote's at y equals 0 because the degree of the numerator is less than the degree of the denominator. We're going to factor the denominator. We find that there's vertical asymptotes at a positive 3 and a negative 2. These are not any common factors with the numerator. To find x-intercepts, we set the numerator equal to 0. So the x-intercept's at negative 1, 0. The y-intercept is at 0, negative 1/6. So these are all the steps you need to graph a rational function. We've found a few more points and graphed it. So they have a solid red line for the asymptotes, but I like to do dashed lines. It distinguishes them, unless you do it in colored pencil, like they've used colors here, to graph the different branches. Okay, let's try our hand at this.